Separable differential equations. A separable equation is a first order differential equation. So first order means having first derivative, just dy over dx or y prime. So we can have second derivative or y double prime. That's not the case. A separable differential equation is a first order differential equation. So differential equation means an equation containing derivative, okay, in which the expression for dy over dx can be factored as a function of x times a function of y. So when we have an equation like this, dy over dx equals a product of some function of x and some function of y, then this equation is called a separable equation. In applications, we model a lot of processes like physical, chemical, biological, and a lot of other processes in terms of differential equations. And to get the solution, we just integrate. After a couple of steps, we integrate and get the solution. And as we know, when we write dy over dx, x is independent variable and y is dependent on x. So one of the examples we've seen is the population growth or bacterial growth, radioactive decay, etc. We saw the following, okay? In fact, the differential equation is dp over dt. This is kind of y and this is kind of x equals kt. P is population, T is time. We did not see this, but when we solve this equation, we get P equals P naught e raised to kt. We've seen this a lot. If this k is positive, then we get exponential growth. If this k is negative, we get exponential decay, radioactive decay. In fact, this equation comes from this differential equation. Now we are trying to solve this type of equations in this section. So when we have a separable, then how to solve? How do we solve? All we have to do is write this in terms of differential form. Differential means move dx to the other side. So dy equals like this. Then separate the variables. Here a function of y, we got dy, so we need to bring f of y to the left side. For here's a product, so we divide both sides by f of y. So we get 1 over f of y equals this. And next thing we do is integrate both sides. Now this integration could be easy or could be very complicated, but in any case we learn a lot of methods in this class. We integrate, then next we solve or isolate y. Solve for y. That means isolate y, and that's our solution. So here in this application I showed you, this p is like y and t is like x. When we solve, we get this. Okay, p naught is initial population or just a constant. So let's do 2 examples, and for more examples you can visit course website. So here is dy over dx equals 5x. First we need to write this in terms of differential. So move dx to the other side. So dy equals 5x dx. Now we need to separate the variables. If we had y, we would bring to the left, but that's not the case, so it's separated. Next we do is integrate. So there is nothing means 1. In fact, 1 dy 5x dx. and we know antiderivative of 1 is x, but the variable is y. This is y equals, and plus c, we'll take care of that in a moment. Antiderivative of 5x is 5x squared over 2, or 5 halves x squared. Now we get plus c in the left side and another constant in the right side. But we can always move that constant to the other side. Those are not same constants, they are different constants. So we need to write plus c1 plus c2. But when we subtract, we can just write generic constant c. And this is in fact solve for y equals this, so done. So the solution for this differential equation is this. Now next, solve the differential equation that satisfies the given initial condition. Sometimes we have differential equation and initial condition. So with this initial condition, we can find the value of c. Okay, like here we had this c. Now that c will be determined uniquely in this question. So let's look at this differential equation. So here we got dy over dx equals 3x squared e to the negative y. Now we write in terms of differential form, which is move dx to the other side. Next dy, so we need to bring this function of y to the left with dy. So here is time, so divide both sides by e to the negative y. So divide means 1 over e to the negative y dy in the left, 3x squared dx. Oh, this negative means we can just move up. So this is same as e to the y dy. So 1 over e to the negative y means just move up, dy equals 3x squared dx. Now integrate. After we separated the variables, function of y dy equals function of x dx, we integrate. And antiderivative of ey is just ey equals antiderivative of 3x squared is x cubed. As you can see, derivative of x cubed is 3x squared plus constant. Now we have two options. We can use this initial condition and find the value of c, then solve for y, or first solve for y, then use this initial condition. I'm going to solve for y. So to solve for y, here is e raised to something, so we need to take natural log both sides. When we take natural log in the left side, natural log and e, their actions cancel, just y survives, and we got natural log of everything. So in the left, y equals natural log of everything. We cannot distribute, okay? Do not try to distribute. Finally, we want to use this initial condition to determine the value of c. So using y at 0 equals 0, that means y is 0 when x is 0. This inside is x. Using this, we get y is 0 when x is 0. 0 cube is 0 plus c. So 0 equals natural log of 0 plus c is c. Now we need to isolate c. Here is ln, so we need to exponentiate both sides. So e raised to left side equals e raised to right hand side. So e raised to 0 is 1, by the way. A number raised to 0 is 1. E and natural log cancel, their actions cancel, c. So c equals 1. Now we go back and plug in the value of c, which is 1, to get the final answer. So thus y equals ln of x cubed plus c. C is 1. Final. This differential equation with initial condition is called initial value problem. In short, initial value problem.